Hello, everybody. Today, I want to just review a little bit of what we talked about last time. And when we were talking about magnitudes, apparent and absolute magnitude, and we said if you know both the apparent and absolute magnitude, you would be able to determine the distance of a star. Well, I want to show you a couple of slides here. You don't have to write anything down. I want to show you the brightest stars in our night sky, apparently brightest, what the apparent magnitude is, and what the absolute magnitude is, and the distance. So you see that the brightest star, like Sirius, the brightest star in the night sky, its apparent magnitude minus 1.4 or so. The absolute magnitude is 1.43. And remember, if you know both the apparent and absolute magnitude, you can get the distance in parsecs. And then what you do is just multiply by 3.26 to get light years. So take a look at these stars. This kind of represents the colors too. Look, blue for a lot of these stars, bluish, white. Very few red stars. Actually, only one on this top 10 list, which actually Betelgeuse has dimmed quite a bit for some unknown reason lately. It's not even top 10 anymore. But there it is. So if you know the apparent and absolute magnitude, you get the distance. That's what we talked about last time. Well, the nearest stars, I think I showed this one to you. Look at this. The stars that are closest to us are mostly red stars. Very, very low luminosity, not very bright compared to the sun. And look at the apparent magnitudes for these stars. Look at them. Yeah, I mean, most of them you would not even see with your naked eye. I mean, Sirius, yeah, and Alpha Centauri you could see with your naked eye. This one is actually a brown dwarf. It's not even it's giving off a lot of infrared, not even really much visible light. So this is actually infrared magnitude, this J band magnitude. And it shows you look at the absolute magnitude here, very, very faint. So these stars are very, very close. Look at the distance in parsecs, but you wouldn't even see these with the naked eye. They're so faint stars. So if we go back, these brightest stars are actually, they're really very luminous stars. But the closest stars to us, we can't see with the naked eye. Now, we did exercise our homework one. That was what we did a couple of weeks ago, turned in last week, possibly, depending on what class you're taking. So we already did exercise. We did homework one. We did exercise 2 in class. You turned in homework 3, hopefully. Well, I'd like you to do this today. All right. By the end of the evening today. By the end of the day today, by 11:59 p.m. tonight, just before midnight, by midnight, I'd like you to do this. I would like you to do this exercise number 4. And here's what it says. Assume you calculate the parallax of a star, Aldebaran, the parallax of the star Aldebaran, by using a photograph. The parallax is to be 0.05 arc seconds, which is 1/20th of an arc second. What is this distance in parsecs and in light years? Now, this is based on what we've did a while ago, a little bit of time ago, where, remember, if you, for triangulation, this is doing triangulation. If you can determine the parallax angle, you can determine the distance of a star, where the distance in parsecs equals 1 over the parallax. Again, I'll say it. The distance in parsecs equals 1 over the parallax. Well, here it is. The parallax is 0.5 arc seconds, or 1/20th of an arc second. So really, it's just 1 over 1/20th, and that'll give you the distance in parsecs. Now, remember what the rule is? If you do 1 divided by a fraction, 1 over 1/20th, you invert and multiply. So it would be the same thing as 1 times 20 over 1, and that would be in parsecs. To convert to light years, remember what you have to do? Multiply by 3.26. All right, so now, second question. The star Betelgeuse has a parallax of 0.01 arc seconds. Not 0.05, but 0.01, smaller parallax than Aldebaran, smaller. Does that mean, is Betelgeuse closer or farther than Aldebaran? So remember we talked about with triangulation, if the parallax is smaller, is that a farther object? Or is it a closer object? You can decide that. Now 3, this is about the Doppler shift. Remember the Doppler shift. Aldebaran exhibits a redshift in its spectrum. What does that mean about it? So go back, look at the Doppler shift. What does a redshift mean? Well, you might as well look at what a blue shift means too. So if something exhibits a redshift in its spectrum, what does that mean? Now, 4. Aldebaran is a relatively cool orange-red star, yet it has a very high luminosity. How can this be? So here's what you need to think about. You need to think about the Stefan Boltzmann law, where it says the luminosity is proportional to the surface area and also the temperature of a body, right? So how bright something is, how much energy something is giving off total, corresponds to how big it is and how hot it is, what the temperature is. So it says Aldebaran is really high luminosity. So its luminosity is really bright, yet its temperature is cool. So if you have a cool temperature, yet you're really, really bright, what is the only way you can accomplish that? What must be true about Aldebaran? It is very, very luminous, but it is really, really cool. So that's an exercise due today by midnight, tonight by midnight. So get that in for full credit. Either you get it in by midnight or it's not worth it. 10 points? 10 points just by getting in by midnight. Write this down, upload it, or send it to your assistant, and that's all you need to do. All right? So now, okay. So let's talk about something else. I want to talk about something very important in astronomy. It has to do with some astronomers here. And there were these astronomers working at Harvard College Observatory in the early 1900s. And what do you notice is true about these astronomers? Everybody here, except for this person, yeah, they're all women. There were these women astronomers who were actually being hired by this director, Edward Charles Pickering. And what these women were doing is, figuring out a lot of stuff. They were analyzing data, just some incredible things. Each of these astronomers was doing a different subject in astronomy, analyzing data from a different thing. And what was happening was this, that they were doing this work. And the reason they were hired, the women at this time, is that they could be hired. They were being hired for half of what they would have to pay men. So Pickering, this person, was hiring women to do this work, astronomy, in half of what he would have to pay men. And that's what was going on. It was an absolute travesty. And they weren't even getting as much credit for their work at the time as they do today. As today, they get the notoriety they deserve. So this is just a travesty. It was going on everywhere at the time. And so it's just as terrible. It doesn't justify it. This person, don't even write his name down. He doesn't deserve it. Edward Pickering, there's the dates he lived. I do not have a high opinion of this person. He was the director. Now, Neil deGrasse Tyson, who I really respect and admire, you've seen him in the new Cosmos series. You'll see some videos of him. You saw the video, the science video, the Science in America. He did the Science in America. I mean, every time Neil deGrasse speaks, I'm listening. I just love the stuff he says. I love how he talked about things. I love how what critical thinking he uses. Well, what Neil deGrasse Tyson said is this guy was not such a bad guy because he was actually hiring women when other people were not. Well, still, if you're only paying him half of what he paid men, I'm not going to. Here's one time I'm going to disagree with Neil on this. I have no respect for this person. If I were to see him on the street, I'd tell him what I think of him. I don't think I'm going to see him on the street. And you can have your own opinion of him. But in my book, he's not in my book. So I'm not going to, don't write him down. If you don't want to look at him anymore, I don't blame you. I think he's okay, I'm just going to move on. Now, here's somebody, one of the astronomers, Henrietta Swan Leavitt. Here is somebody worth writing down, Henrietta Leavitt. And there are the dates that she lived. Don't worry about, I'm not going to ask you dates in this class, but write down Henrietta Leavitt because she is responsible for doing something that changed astronomy in the 20th century. So it was just a remarkable. So here's what she did. Let me talk about her a little bit. And she was actually studying a type of star that was called a variable star. A variable, a star that actually changed in brightness. it changed in brightness to the point where it actually, over days, you see it kind of getting brighter and fainter. Now, most stars don't do that. Most stars are stable stars like the sun that stays the same every day, like the stars, most stars up there. Sirius is pretty much, stays the same every day. I mean, most stars do that. But there were some stars that got brighter and fainter. And sometimes it took them days, a few days to get brighter and fainter. Sometimes it took them, hundreds of days to get brighter and fainter. And these are called variable stars. Now, at the time, they didn't know why this was the case. It turns out the reason is they're dying stars and they're unstable. And the first one that was discovered that Leavitt was studying, Leavitt was studying a certain type of star, and it was this star right over here. It's a constellation of Cepheid the king. You may have heard of Cepheid, the husband of Queen Cassiopeia, the father of Andromeda, the princess. So Cepheid the king. No, that's not necessarily that important right now, the constellation, but the name of the constellation is because this star, Delta Cepheid, this star was a variable star. And because the first one was discovered in the constellation of Cepheid, every time we find a star that's getting brighter and fainter, like this one, we call them Cepheid variables. And this was what Leavitt was studying. She was studying a star called Cepheid variable to figure out what's going on and why is it doing this? Why it's doing this, but to see get any information about these stars. Now, something looks off over here. So what she was studying, if you want to write this down, this is a good thing to write down. She was studying these stars called Cepheid variables. Again, Cepheid because the first one was found in the constellation of Cepheid. These stars got brighter and fainter. Now, let me show you this. It turns out that some of them took a longer time to get brighter and fainter, which means a longer period. And she was figuring, what she figured out, what Leavitt figured out, is that the ones that took longer to get brighter and fainter, which called this pulsation period, actually were brighter on average. Now take a look. What if one only took 20 days from brightness to brightness? That would be called this period. She found out this relationship where she'd come up on this curve, when she created this graph, and she'd come up here where it hit this line. There was this line. And she'd come over here and it says it would be an absolute magnitude of -5, which is pretty bright. But one of these stars, another variable that took 70 days to go from brighter to fainter, you come up to here, it would have an absolute magnitude of -6.5. Isn't -6.5 brighter than -5? Remember, the more negative, the brighter. So the longer the period, the brighter on average the star was. The longer the period, the brighter. This is called the period luminosity relation for Cepheid. The period is just the time from brightness to brightness. Luminosity is just another, it's kind of like absolute magnitude. Remember, absolute magnitude, true brightness is a measure of luminosity. So the longer the period, the brighter. She figured out this relationship. Now, look at this. Now, what was done with this? Now, you do not have to write this down. So what could be done at this point? You had to determine the apparent magnitude of a Cepheid variable. Just by watching it, looking at it, you could determine its apparent magnitude. That's easy. You could do that with your eyes or, taking a picture, a light. So you determine little m from the period, which you can get from a series of photographs. You can get a series of photographs. You can get its period. So from its period, you can get its luminosity or absolute magnitude. So look what you have. You have the apparent magnitude and absolute magnitude. Now that you had both its apparent and absolute magnitude, you could determine its distance. So what Leavitt did is figure a way to determine the distances of these variable stars, these Cepheid variables. Again, I'll say it again. From apparent and absolute magnitude, from the period, she was able to get their absolute magnitude. She was able to figure a way to get the distances of these stars, or actually a way to get if you get the apparent and absolute magnitude, you can get its distance. So she knew now, then other astronomers figured out that from her work, this period luminosity relation, because you can get its absolute magnitude and its apparent magnitude, you can get its distance. Now we got to talk about, here's someone you have to write down. Here's someone that's worth it. Edwin Hubble. You've heard of Hubble, I'm sure, the Hubble Space Telescope. So write down Edwin Hubble. What he did is he was studying with a giant telescope in Los Angeles area, Mount Wilson. He was studying this thing called the Andromeda Nebula. Now, At the time, in the 1920s, and before that, in the early 1920s, it was only known that there was one galaxy. I mean, only the Milky Way. There were other galaxies known. It was thought the whole universe was the Milky Way galaxy. Well, now, they did see these things in the sky look like structures, but they didn't think these were anything other than these things called spiral nebulae, things in our galaxy. Things in our galaxy. Well, what Hubble found in the Andromeda Nebula were these variable stars. And from Leavitt's work, he was able to compute their distance by getting the period. And then these stars were incredibly faint. I mean, you need a telescope. So they were incredibly faint, like apparent magnitude of 20. Apparent magnitude, remember, apparent magnitude of 20? That's faint. But when he figured out from their period what their absolute magnitude should be a -6. Now, how could he explain something that looked incredibly faint? You need a telescope to see it. Yet, if you put it at 10 parsecs, it would be a -6, like one of the brightest things in the sky. The only way to explain that is got to be far. And Hubble calculated these stars were over 1 million light years away. Now, the galaxy was not known to be that big. The galaxy was only to be, I mean, relatively small compared to that. So if these stars were that distance, over 1 million light years, it meant this thing that they were in, this Andromeda Nebula, was over 1 million light years, which meant it couldn't be a nebula in our galaxy. It had to be another galaxy. So what happened is that the Andromeda Nebula, again, had very, very faint Cepheid variable stars with a very apparent magnitude was faint, but their absolute magnitude was bright. What did that mean? The Andromeda Nebula was not a nebula, but another galaxy. And without Leavitt, he couldn't have discovered this. Without her period luminosity relation, he would have no way to determine the distance to these variable stars that allow him to determine the distance to the Andromeda Galaxy. And then he discovered all these other spiral nebulae that they thought were things within our galaxy were actually galaxies. The universe was bigger than anybody had imagined. In one night, the universe went from being the Milky Way to billions of other galaxies like the Milky Way. This was maybe the most incredible thing in the science, well, at least in astronomy, in the 20th century. And, of course, Hubble was able to do this. But guess what? Without Henrietta Leavitt, there's no way Hubble could have done it. So Henrietta Leavitt is incredibly important in figuring out about our universe, about the size of our universe. And Hubble, of course, was too, because he kind of followed up on it, but without Leavitt, Hubble couldn't have done what he did. There was a play on the life, I think it was, 6th Street Playhouse, 5th Street, and kind of in Santa Rosa, I think it was called Silent Night, and it was a great play about Leavitt's life, Henrietta Leavitt's life, and it was very interesting. This was a few years ago. Now, okay, I didn't want to show you that. My PowerPoints are kind of messed up here. But I want to tell you something that's really important for stars. Actually, the most important property of a star. The most important property of stars, currently showing here, happens to be mass. Mass is the one most important property of a star. Mass of a star can determine whether if the star actually becomes a star, whether it becomes something called a brown dwarf if there's not enough mass, whether the star becomes a star like the sun, or much more the color of the star. Mass determines how long the star is going to live. Mass determines the size of the star. Mass determines the temperature of the star. Mass determines how the star is going to die. Mass determines whether the star is going to blow up or not when it dies. Mass determines whether the star's core is going to become a white dwarf neutron star or black hole. Mass determines everything. Do you know what we're going to say? Mass is the most important property of a star. Mass. Well, now, if mass is the most important property of a star, wouldn't it be nice to know what mass is? Because a lot of people say, oh, all right, mass, most important property of a star. What does mass mean? Now, let me ask you a question. What is mass? Is mass the same thing as size? No, it's not. Is mass the same thing as density? No, it's not. Mass is really not the same thing as anything but mass. So what is mass? Mass, very simply, is stuff. Write this down. Stuff. Substance, if you prefer. The amount of material something has. But in other words, mass is just how much stuff something has. Mass is stuff. stuff. And what kind of units do we use for mass on Earth? Well, usually we use units like kilograms, grams, right? 1,000 grams is a kilogram. We use milligrams for medication. 1,000th of a gram is usually what is mass, a milligram, which usually medication is in milligrams. But mass units are usually grams, kilograms, and 1 kilogram mass weighs at the surface of the Earth. If you have 1 kilogram, about 2.2 pounds. So if you were to pick up a weight, now think about this. Think about this. If you pick up a weight on Earth, you know, like a weight that you put on a weight, like this disc weight that has listed on it. It has two things listed on it. It has the number of pounds, and it has its mass. So if you pick up a weight that says 3 pounds, but it also says about 1.4 kilograms. Let's say it says 1.4 kilograms, 3 pounds. Well, the 1.4 kilograms is the material. It's the mass, how much stuff it has. The 3 pounds is its weight, but its weight changes depending on how much gravity there is. If you took that 3-pound weight into space, it would be weightless. It wouldn't weigh anything, but it would still be 1.4 kilograms. So weight is how much gravity pulls on your mass, but mass is how much stuff you have. So I'm going to say this right now, and something good to write down. If I gave you a weight and it said 3 pounds and 1.4 kilograms, one of those is accurate and one of those is not. Well, the 1.4 kilograms is always accurate. The 3 pounds is not. So what they're assuming is that you're going to be working out at the surface of the Earth, and usually they're right. However, if you were to bring that weight to the moon, it would still be 1.4 kilograms, but it would say something like half a pound. It should say half a pound. So you see your weight changes depending on how much gravity is pulling you down, but your mass does not change. You go out into space and are floating there, you're weightless. You weigh 0 pounds, but you still have your same mass. So mass is hard to change, all right? So when you're saying you want to gain weight or lose weight, it's not really weight you're trying to gain or lose, it's mass. And if you can gain or lose mass, you're also gaining or losing weight. All right, so now let's talk about how important this is with stars. Because what we can do is determine the masses of stars by watching stars going around each other. There's a famous equation called Newton's version of Kepler's third law. You don't have to write this down. I might show it to you somewhere. It says the mass of one body plus the mass of another body. If you're talking about, let's say, 2 stars going around each other or a planet going around a star. So again, the mass of one body plus the mass of another body is equal to p squared, or a cubed over p squared. It's equal to a cubed over p squared. Now don't write this down. A is just the distance between the bodies. P is period, the time it takes to go around. So there's a famous equation that says the mass 1 plus mass 2 is a cubed over p squared. And this is a way we're able to determine the masses of stars. So again, a way we can determine the masses of stars. Now let's talk about the masses of stars. We have a unit we use. And here's something that I'd like you to write down. Because the mass of a star is very important. We want to know the mass of the stars. The mass of the sun is about 2 times 10 to the 30th kilograms. I don't need you to know that. That's an incredible amount of mass. I want you to know it's called 1 solar mass. I want you to know it's called 1 solar mass. So 1 solar mass is the mass of the sun. Here's the symbol. I don't know, that should be a circle there. Kind of looks like a sigma. So 1 solar mass is like a circle, 1 with the symbol for the sun, and that means mass. 1 solar mass. So that's 1 solar mass. Should be a circle with a dot in it. Now here's something you should write down. Well, good. The sun's mass is 1 solar mass. Stars range in mass from 0.08 solar masses to 320 solar masses. Again, this is it should be a circle there with a dot. I don't know. This font has gotten a little strange here. The most massive single star discovered is 265 solar masses. You don't have to know that. So we're going to call the mass of the sun 1 solar mass. Distribution of stars by mass. Now, don't write that. Don't write this. I have a better one for you. I have this one. Look at this. And you're not going to have to know this, but just listen to this. It says, for every one star with a mass between 20 and 320 solar masses, and that's a lot, that's a high mass. I mean, think about that. If it's between, that's an incredible amount of mass. If we find one star like that, and these colors represent kind of the color of the star, there would be 4,400 stars with a mass between 3 and 20 solar masses. And again, the font is bothering me. I've never seen that before. That symbol there. It should be a circle with a dot in it. So look, you know what this is showing you? This is showing you, remember this rule where if you have a very, very massive thing, there are a lot more lower mass things? Potato chip rule. So look, if we find one star out there with this, in between this and the mass, that's an incredible amount of mass. There are going to be 4,400 stars approximately with a mass in this range. I mean, that means if we find 2 stars in this range, between 20 and 3, we got 8,800 stars here. You see, this is not the number of stars out there. It's a ratio. It's a distribution. It's showing you for a very, very massive star, there's a ton of lower mass stars. And look, for every 1 star in this range, 4,400, there'll be 4,400 stars in this range. There'll be 20,000 stars between 1.5 and 3 solar masses. There'd be 100,000 stars with a mass between 1.1 and 1.5 solar masses. There will be 253,000 stars with a mass between 0.85 and 1.1 solar masses, like the sun, right? The sun is 1 solar mass. There'd be 400,000 stars with a mass in this range, and 2.5 million stars with a mass in this range. So the lowest mass stars are these red dwarfs, about a third the size of the sun, very low luminosity, but those are the most common. And you don't even see those. You go out at night, you can't see them. Why? Because they're low luminosity. They're very, very faint. So when you go out at night, I say you're going to probably see more like stars like this. You might see some like this, but these are rare. Look how rare these are. Even though there are, I mean, incredible amount of these, but for an incredible amount of these, there are going to be so many more of these. So here's what I want you to know from this. For the lower mass stars, if it's a lower mass star, there's going to be more of them. And if it's a higher mass star, there's less. Just like it's a potato chip rule for stars. Potato chip rule for stars. Now look at this. What about objects with a mass lower than the mass of a star? How many would there be? Well, there would be more than this, right? And how about a even lower mass than that, less than 1/100th of the solar mass? There's going to be even a bigger number there, a bigger number here. So this is a potato chip rule. Now look what we call these. You don't have to write this down now. But if there's something in a range of this, lower than the mass of a star, they're called brown dwarfs or failed stars. Should be hundreds of millions of those for every 1 star that's between 20 and 320 solar masses. And there should be billions of these objects less than 0.01 solar masses, and we call these planets, like the Earth. So there should be more planets than really anything out there, right? I mean, minor planets are included, major planets, minor planets, dwarf planets. There are going to be tons of those compared to stars, and there's enough stars. So this is a potato chip rule. Now, I'm not going to talk about Cannon yet. Cannon is important. Cannon is great, but we're not talking about Cannon yet. So that's it for right now. I will post another one of these shortly, talking about Annie Cannon and what she did, and that is it for now.